Okay, the next presentation will be given from Marino. Marco is with the Solaris SRL, and he is presenting together with ENI. So, Marco, the floor is yours.
Right. Thank you, ladies and gentlemen. Good morning or good evening, depending on where and when you are looking at this. Thank you for being here today, and thank you to the other presenters who gave out very interesting topics. This technology is somewhat a little different, but similar in some aspects. Last time I was here in this room, it was a couple of years ago, I was talking about illegal tapping. So everything was centered about illegal tapping because the technology was born just primarily to solve that problem, which was not the only problem. Thing is, it worked very well. It cleaned our country, Italy, home country, so they were stealing more than 100 times per year, and now they're not stealing anymore, 0. So today, what I will present you are some other applications, because in the meantime, we found out that the system can do many other things. So, my name is Marino, I'm the CEO of Solaris, which is a joint venture between 2 Italian companies, Solgeo and Aresis, and we are official licensee of this technology from ENI. The technology was patented and developed by ENI over the last, I would say, 15 years already to protect and monitor oil and gas pipelines in a lot of scenarios. It's non-invasive. This is the actual sensor that we are using, so all that we require is an existing fitting, it's an existing hot tub. Typically, we don't even have to create new hot tub. It's particularly effective in the brownfield. So, as you can see, it's very easy to install. We have a portable version which can be installed in minutes. But what does it do? It can detect against intrusions, leaks, spillages, impacts on the pipeline, but not just leak detection, as you will see in a moment. It is so evolved at this day that we call it a family of technologies, and every year we're adding something more. So, sorry, I just pressed the wrong button here. So, what is the working principle of vibroacoustics? And what is exactly our definition of vibroacoustics? It's a combination of pressure, micro-vibrations, and sound. 3 technologies instead of 1, always captured at the same time, at the same moment, instead of a single one. It works with a multi-point network of sensor. You have to install a sensor up to 50 kilometers apart, so you really need very few sensors to cover even very long distances. And on the other hand, you will get several different performance levels according to the distance between the sensors. This is an example of one of our interfaces, and it responds in real time, less than 10 minutes, even less in some dedicated scenarios, and with less than 25 meters accuracy. And we have had many success cases with less than 1 meter accuracy that depend on several factors. Today, we protect more than 1,800 kilometers of pipelines all over the world. For example, most notably, we protect 100% of the finished product network in Italy for ENI, but also for other customers. We are very active in the country of Nigeria, very challenging environment, I would say, where we protect the delta of the river Niger. And then we work also in South America, Brazil and Argentina mainly, but we're entering also in other countries. So we acquired experience over a wide variety of pipelines, buried, unburied, onshore, offshore, crude oil, refined products, also water and also gas. We are started working with hydrogen too and with CO2. We can work pretty much with any pipeline diameter, any pressure range up to 300 bars, also mixtures or liquids or gas. So I already told we have a wide variety of cases. And the distance between the sensors, that depends on the performance. It will be very clear on the next slide. We integrate with existing equipment, SCADA or DCS, but we're not a purely software-based solution. We provide also the hardware. So basically, we provide both the vibroacoustic sensor and the software. We support a lot of protocols already. The most interesting feature of the system is that we have actually no limitation over the minimum detectable leak quantity. We can even detect half a can of product going from the pipeline. What I typically do when we do the leakage test, the spillage test, we challenge them to spill less than a can of product. It's very difficult, trust me, if the pipeline is in pressure, it can be done. It will be detected and localized. And it's very effective when we do the demonstration. The false alarm rate is negligible. It's very, very low for something related to physics here about the vibroacoustics and the fact that you are using 3 technologies together to cross-validate, and already told about you the accuracy and the response time. So we were talking about the distance between sensors and what you can see. This is a family picture. It's for this year, so it was recently updated. Let's say that if you're able to put the sensors every 50 kilometers, which is the advised maximum distance that you should use, typically is lower, let's say between 20 and 30 kilometers, because as you might understand, since you can profit, you can benefit from existing derivations, you might want to use existing valve stations. And typical distance among valve stations is 15 to 25 kilometers in a lot of areas where we work. Sometimes it's up to 50 kilometers. You can go even farther, but that will reduce the performance for leak detection. So what are you able to do with the LD version of the system? You will be able to detect leaks, impacts, especially of the forming type, and many precursor events. So, what are precursor events? Those are defined by us as the preparation activities before an illegal tapping takes place. You have to drill, you have to weld, you have to braze, you have to install your derivation. We can detect this activity even if there is no leak yet. This will give time to the pipeline operator, time to the customer, time to the police. In many cases, the police intervened before the actual leakage took place. It was in hundreds of recorded cases for us. In gases, because of compressibility, you have to stay at a short distance. So I would say 10 kilometers is a safe bet. All the systems, and these two can do other things, I will talk to you in a moment, but what happens if you can reduce the distance much more? You get the LD plus TPI function. The distance among the stations is much lower. We're talking about just 5 kilometers, but you get something very similar to what the optical fiber can do without the need to lay the optical fiber. So this is the strong point of the system, because we can detect, we train the system, we calibrate the system to detect manual digging along the right of way with shovel and pickaxe. I have some examples on the next slide. The two systems can work together on the same pipeline, on the very same pipeline. Even sections can be covered with LD plus TPI, and the whole pipeline can be covered with LD. So you can protect hotspots or dangerous areas with one technology and not with the other one. Last but not least, the LD plus mass balance. So we integrate measurements coming from existing flow meters, typically, or we can provide additional flow meters to close the circle. So not just vibroacoustics, but it's vibroacoustics integrated mass balance technology. So you can benefit from a fully integrated system. It's not a standard mass balance model, it's an enhanced model with also information coming from vibroacoustic sensors, which are located along the pipeline. The other interesting thing I will mention today is the other things that the system can do. We can do peak tracking very easily. We can, and you will have an example today, perform assessments of the sealing grade, of the sealing status of inline valves. So we can actually tell the operator if their valves are leaking or not internally using vibroacoustics. Also, land movement assessments, we can detect earthquakes, for example, and some other things that we can do. So this is the basic difference. When you have both systems, the TPI and the LD plus TPI, you can anticipate the leak, you can anticipate the threat. So potentially you could even see someone approaching even, again, with that fiber, but we concentrate typically here on detecting digging, hammering, hitting, welding, and eventually spilling. But when you are spilling, you get another kind of alarm. So we are able to give the operator several degrees of alarms, and they typically follow a precise timeline, especially in case of illegal tapping. So you get an orange alarm if somebody is digging, and a red alarm if somebody is spilling. So you get to know the difference. This is an example of what we detect. These are manual digging activities. So Each stroke on the ground will transfer energy, mechanical energy, from the digger. These are all real experiments that we did. This energy will propagate to the ground, then to the pipeline shell. Eventually, it reaches the fluid, but just at the time when it reaches the pipeline shell, we can detect it, but when it reaches the fluid, we can detect it even better. It travels 4 kilometers in both directions, and we can detect it without false alarms, because we train the system to look for these specific activities, for their signature, for the time duration, for their characteristics on the ground. We are really good in sorting out what is, for example, trains passing by, cars passing by, or somebody digging where they're not supposed to be digging. Same thing happens for strikes, for impacts. With bigger impacts, I'm talking about deforming impacts, even if there is no leak. For example, suppose an excavator denting the pipeline, you can use the LD system, no problem. But if you want to detect very small hammer strikes, you have to use the LD plus TPI. And these are all real events. You can really distinguish each and every single strike there. This is an example of the activities we perform on the field to calibrate and stress test the system. Basically, here, we make people dig. This is, of course, part of our test. You can see it's pre-dug for safety reasons, otherwise it would collapse. We perform hammer strikes, and also the calibration is really interesting because we use a calibrated weight that adds a known amount of energy to the ground, and we are able to detect this from kilometers of distance. So, what do you need to install the systems? 3 things. Power. It can be solar power, direct power, any other power form, less than you give about 20 watts to our system. For example, we are working a lot in South America. We are installing a lot of solar panels to be self-sufficient. When we work in some areas where sun is a little problematic, we use, for example, fuel cells. We can use whatever combination, and we can provide turnkey solutions, so we can solve this problem for the customer. Then we need communications. So as you can imagine, the technology requires a data streaming from the sensors to the central processing server, happening in real time. It can also happen offline, but you lose the magic of intervening in real time in this case. We're talking about less than 20 kilobits per second, so we can work with satellite, we can work with ADSL. Typically, we work with UMTS, 3G or 4G, whatever we can find. Last, but it's actually the most important, you need fluid to be on the pipeline. So the information from the leakage, it's easy to understand when you have the optical fiber, the information travels on the fiber, but in this case, the information is traveling mainly on the fluid. If the pipeline is empty, there is no leak detection system. So at least 1 bar. The pressure doesn't need to be that high, but at least 1 bar. These are typical installations of sensors, so we do not need to touch the pipeline. That's the important thing. We can use an existing derivation. This is a bypass. The pipeline is buried 3 meters under the ground, so that's why the installation is non-invasive. You can make use of existing valve stations, protected as you wish. Of course, everything is EITEP certified, and I already mentioned the portable version of the system that we have for test and demonstration that we can carry all over the world. A newcomer in the family is what we call the shallow water sensor. You can come see it in booth A3, right at the entrance of the exhibition. Is a fully variable, a fully submersible, up to 10 meters, but the inner core is certified up to 1,000 meters. So, but up to 10 meters you can install, for example, this was designed for swamp areas, where you are able to temporarily dry the area to allow for a correct installation. You still have a cable going to an acquisition unit, which has to be placed at less than 1 kilometer distance, but still this allows you to conceal the sensor for security reasons. It has much lower maintenance with respect to the other sensors, even if the maintenance requirements are very low. We're talking about once adjusted maintenance per year. Basically, the only problem is the area must be temporarily dry, otherwise it's a very robust solution that, again, we're using in swamp areas in difficult territories, like, for example, the Nigerian jungle. So, other things that the system can do. This is an example, besides just leak detection, of what we can do. One thing is peak tracking. The interesting thing is that we can track the peak, not only track the peak in real time, but only classify impact points. So if there are unexpected impacts from the peak impacted something, an existing derivation at the end that was not supposed to be there, we can pinpoint the exact locations of such impacts and make an analysis. And this is very important. The most interesting thing is that we can track the peak even if it is stuck in the pipeline and it's too late. So you call us after the peak was stuck. We have techniques, reflection-based techniques, allowing us to exactly locate the peak without any kind of problem. Earthquakes detection, so it's pretty easy with the sensitivity of this system to detect earthquakes, but this is a real earthquake, happened at the end of 2019 in Albania. We detected it in northern Italy, in Mantua city, for those who know. It was a strong one, 6.2, so some of you might remember it. Basically, we can choose whether we want to raise an alarm or not to the customer, so the customer can choose actually. But typically, everybody wants to receive an alarm because they then can call us and we can make an assessment for the damages. Of course, the system is 100% automatic, but they can call us. So, besides earthquake detection, there are other things that we can do, for example, monitoring the working and the operating conditions of the equipment on the pipeline without even touching it. For example, this is a difference among a broken pump or a well-working pump. So spectrograms showing you that there are changes in the way the pump is rotating, for example. It's very easy for us to detect in real time. And this is something that we also do, especially over time. After a few months, the system is installed. A very brief, before going to the conclusion and presenting you some cases that I presented in the paper that you will find in the next publication of the Pipeline Technology Journal also. A very general and rough comparison is absolutely non-exhaustive among EVPMS and other technologies. Basically, EVPMS can work very well for prevention. So it does some things very similar to the optical fiber when it is used in the LD plus TPI mode. It's really fast to respond here, can detect and classify also no-leak events. So this is mainly the biggest difference. With respect to the optical fiber, it does not require the laying of the fiber itself, again. But it's also useful for intervention like the others. The most notable point is that not only we can discriminate a leak versus no leak, but the minimum detectable leak quantity is 0, or even fraction of liters. So some customers are very impressed when they do the testing that we are able to detect when they create or they prepare the tapping for the controlled spillage, for example. This is another interesting thing. And we can perform other tasks like peak tracking, failure detection. Other technologies can do a limited subset of this, but this is also, I would say, interesting. Now, I will finish with 3 cases that they are, again, in the paper we presented at this conference about integrity management, pipeline assets reuse, and energy transition. Basically, those are these 3 very important topics that we wanted to point out, because we found out that we can provide a lot of information, especially during tough times like this, where the pipeline is a very reliable asset, is a very valuable asset, and you do not want to miss the opportunity to reopen old pipeline, to reuse old pipeline, or to make another destination of use to your existing pipeline, for example, for transporting CO2 or hydrogen. So, first case, localization of an existing leak during a pressure test. We assist a lot of pressure tests. We are talking about the need to detect very, very small holes, sometimes in cases where there is no EVPMS system. This is a case with portable EVPMS stations, so the customer called us to assist during a test. This is in particular a pneumatic test, and was able to detect a 25 square millimeters hole originated from corrosion on the pipeline. The smallest we detected with this technique was less than 1 millimeter in size, so very, very small holes. It's not about detecting it, because during the pressure test, it's typically very easy to detect this kind of holes. It's about telling where they are. And this was done very, very precisely, very low localization error. We were talking about a few meters, as you can see here. The second example is the detection of microvents in a pipeline before reactivation. This is, let's say, a consequence of COVID-19 pandemic, which caused a temporary stop of some pipelines. This is a pipeline, an actual pipeline located in northern Italy. It was already equipped 90 kilometers. The distance between the station is again about every 30 kilometers, typical installation. In this particular system, EVPMS was already installed. So they asked us, okay, they told us we had to stop the pipeline for several months. Now we want to operate it again. Could you please check if everything is all right? So if there are no leaks, if nothing happened, and we did. Again, with pressure meters, very precise pressure meters, you can already tell there is a leakage. We are talking about this is 6 in the morning, this is 6 in the afternoon, and this is 24 hours. Can you see that the drop in pressure is 0.2 bars, so it's very low, but they are not aligned. So we are not seeing effects of thermal compensation, we are seeing something else. This is before fixing. The leakage is detectable because you know there's something wrong by looking at this. Maybe you're not sure, but not localized. With EVPMS, we localized it. There were very tiny little bubbles coming from a loose fitting after all the time. And the verification step, they fixed the problem and the pressure was okay. Can you see that the time scale here is even longer than this one? So, and this was really effective. The last example is this one, the monitoring of valve tightness. As I told you before, this is something we can do. We can tell the customer if valves are leaking or not, if the sealing rate is correct or not. And this is especially useful in case of life extension analysis. So you want to know, the pipeline operator wants to know if the pipeline is still solid, is still working, and if the valves are leaking or not. Otherwise, they have to change the valves. So the concept here is easy. You have a valve that you want to test. You have two EVPMS sensors, one before, one after the valve. You generate a wave. It's like what we do in the radar world. So it can be any kind of wave. In this case, it was generated by control leakage, but that's not always the case. This is maybe the easier case. So this is the real setup that we use. On valve V11, we created the signal. We recorded it on VLM13, and you can see this is the actual signal going up and down, opening and closing of the valve, very, very short, talking about seconds. And then this valve was completely closed. So in the eyes of the customer, it was perfect, it was sealed. But the other sensor recorded something, and you can clearly see its signature here. But look at the scale. It's several orders of magnitude, at least one order of magnitude smaller. So you can still listen to it, but it is there. It is there. It is very small, but it is there. It was not supposed to be there with a perfectly sealed valve. So the comparison among the waves give us not just the qualitative information, but also the quantitative information. We can tell how much is leaking or it is not leaking. And this was the final case. So I hope it was interesting for you. And if you have any questions, I'm here for you.